Hi, everybody. Welcome to our next round of IRIS-HEP Fellowship presentations. Up first, we have Baidyanath Kundu, who is mentored by Gordon. Gordon, do you want to give us an introduction to Baidyanath, please?
Sure. It has been my absolute pleasure to work with Baidyanath Kundu, who's from the Manipal Institute of Technology in India. He's an undergraduate there, majoring in computer science and engineering, and has been working with me on reading the CMS Run 1 miniAOD files, which are found in CERN Open Data, using the ServiceX backend and FunkADL. Take it away.
Hi everyone. As you know, my project is reading CMS Run 1 and 2 miniAOD files with ServiceX and FunkADL. So let me dive into it. This is just a brief introduction to my project. It was mainly related to FunkADL XAOD package. It was made to support Atlas XAOD, and my goal was to make it support CMSAOD too. For this, we were using the CMS Higgs discovery demo as a guide. I know that most of you might be unfamiliar with some of the terms used on this slide, but bear with me. Like you will understand this in the slides to come. So before we dive into my project, let me talk about ServiceX. The picture that you see on the screen is the LHC plan before the pandemic hit. And the boxes underneath, the yellow ones, they represent the order of the amount of data that is produced in each run. So run 1 had produced about tens of TBs of data, run 2 about hundreds of TBs, run 3 the order remains the same, but it will produce about twice the amount that is produced by run 2, and run 4 and 5 is supposed to produce petabytes of data. Now that much amount of data cannot be processed in a personal computer, and doing it in a short amount of time is very hard. So that's why ServiceX was invented. So ServiceX is a data extraction and delivery service. As shown in the diagram, it takes in data from various formats like XAOD, NanoAOD, and then shrinks the data based on the query given by the user, and then outputs it in formats such as data frames or awkward arrays. So this is the architecture of ServiceX. Now there are a lot of components to it. I can't explain all of them, but let's first look at it through user's point of view. So user will submit a query through a Jupyter notebook, and that Jupyter notebook will contact the ServiceX web endpoint and send the query. The ServiceX web endpoint then processes the query and shrinks the data that the user has requested to the format that he has requested, and sends back the data to the Jupyter notebook. So while this is happening, the user can monitor the request through a web dashboard. My project was mainly related to the code generator part of the architecture, and I'm going to dive into it. So this is the input and output of code generation. The input is a query code that you can see here. This is a real example of a query code that ServiceX accepts, and this is the generated code from that query code. The query code is in Python and the generated code is in C++. This is like a general pipeline of code generation. The query code first is converted into Python AST, and this AST is extended by FunkADL to add link support. If you don't know about link, it's similar to SQL, and then the AST that is produced is traversed by FunkADL XAOD, and it transpiles it into C++. So this is the query code, and this is the AST that is generated by the query code. You can see the select, mini select. These are parts of link, and Global muons, track muons, these are specific to CMS software stack. So this is the query code running on Jupyter Notebook. You can see it's the same query that has been used in the previous few slides. And this is the output produced by the query. It is plotted by using HIST. The notebook is present on GitHub and can be accessed through the link on the slides. So let me talk about the approach that we followed. Our approach was pretty simple. The first step we took was to identify the similarities between the two formats, that is the Atlas XAOD and CMS AOD. Now, a lot of physicists believe that the Atlas and CMS sites are completely different. If they switch from one side to another, will have to relearn everything, and so they are very hesitant to do that. But at least on the software side, we found that they were shockingly similar, and that's why we had to reformat the existing code, so that we could separate the common code and the code that is specific to each format. This was necessary so that we don't end up having a lot of code duplication, and we were able to do it without breaking anything. The next step was to add the code required to support the CMS AOD format. And finally, we had to add the type information for CMS AOD format. So this type information is required so that FuncADL can take the query and understand if the query is right or wrong syntactically. Okay, so the challenges that we faced were that me and my mentor had very little familiarity with the CMS software stack. We had to go through online tutorials for it, and whatever we couldn't understand, we had to ask these guys for it. So thanks to Freya Blackman, Jim Pivarsky, and Brian Cruz for the help they gave us. We also had some time zone and technical issues. Me being from India and my mentor being from the US, we are almost opposite, and we are at the opposite ends of the world. And so there was some scheduling problems, and there were a lot of technical issues faced, like my audio wasn't good and sometimes my network had problems, etc. And of course there was COVID, which we all have faced. Finally, I would like to talk about the future work that we can do. One of the future work that is very important is to add validation files or good run file support. It's called validation files on CMS side and good runs on the Atlas side. They are used to find the good, basically the good runs that are present in the data set. We also have to add more type information for CMS AOD functions. The type information is added on a need-based format and not on, we don't dump everything. So we are still adding more information day by day. And the last thing that would be great to add will be support for more formats. For example, Atlas XAOD Run 3 format. Currently Run 2 is supported, and Run 3 would be a great addition. Thank you. If you want to experience a live demo of the talk of ServiceX, you can come to our IRIS-HEP talk. Do you have any questions?
Really nice talk. Rob, are you there? Because
Yeah, I'm here.
Okay.
Does anybody have any questions for Baidyanath? Going once? None? Okay. Thank you, Baidyanath. That was great. Appreciate the effort, and thank you, and thank you, Gordon, for your mentorship. Okay. So up next we have Jayjeet Chakraborty, and he was mentored by Carlos Maltzahn, Ivo Jimenez, and Jeff Lefebvre. Sorry, I'm probably butchering that last name too. Jayjeet, whenever you're ready.
Yeah, sure. So hi everyone. My name is Jayjeet Chakraborty, and I was mentored by Dr. Carlos Maltzahn, Dr. Ivo Jimenez, and Dr. Jeff Lefebvre for this season of IRIS-HEP fellowship. So I recently graduated from college in CSE major, and I am joining as a PhD student at UC Santa Cruz this fall. And my project for IRIS-HEP was mainly building SkyhookDM and also integrating it with Coffee. So yeah, so what was the problem that we were running behind? So it's the new problem that has come up with high-speed network devices and storage devices, like network devices with 100 gigabits and storage devices like NVMe. The IO layer is no more a bottleneck. The CPU is the new bottleneck now. And this has been mostly noticed in cases of big data processing systems, where highly encoded file formats like Parquet, ORC, when these file formats are required to be decoded on the client machines, the CPUs are exhausted really quickly. And so what happens that instead of having a distributed setup in front of us, like a distributed set of storage nodes, some processing nodes, since the processing happens on the clients, it falls short of CPU available. So that hampers scalability. So one solution to that problem is that we can take away all the CPU load from the client and just distribute it amongst the storage layer. So we offload the computation from the client to the storage layer. In this way, what we achieve is that we can easily utilize the idle CPUs of the storage systems for increased processing rates and faster queries, and also result in less data movement across the system. So if we process more data very earlier in the query stage, so we transfer only the bare minimum required data to the client, and that releases a lot of network bandwidth and also increases performance, as we will see in the results next. So before I go into deep with Skyhook, there are some prerequisites for understanding SkyhookDM. So one is Ceph. So what is Ceph? Ceph is basically a distributed storage system. The heart of it is a distributed object store. It just stores objects in a flat namespace, and it is exposed in three formats, like in three interfaces. So one is a S3 compatible REST interface, and another is a block device interface, which you can like mount. And also another is a POSIX file system interface. And the main selling point of Ceph was that it has no central point of failure. So the clients use a mapping technology called Crush, which allows clients to directly know of where objects are located in a distributed in the different storage nodes, and talk directly to the storage nodes without going via some manager or admin node. So that makes Ceph planet scale basically. And the other thing that makes that for which we use Ceph is that it is highly extensible. So the object storage layer, the bottommost layer, it is highly extensible through plugins. So you can write some code in C++, and that allows you to extend the functionality of the objects. So it allows you to directly access and manipulate the objects inside the storage nodes basically. So yeah, that's in a nutshell about Ceph. Then is the new hot technology called Arrow. So Arrow is a in-memory columnar format for storing tabular data sets, and it stores data in memory in a format that is also same on the where, and that and it also supports several efficient query processing technologies like vectorization and SIMD optimization. So it's really fast on modern hardware. And yeah, the main thing is that without arrow, when arrow was not there, like without a arrow type format on a particular node, if there are different systems, for example, maybe Spark is reading data from somewhere and it is exposing it as a pandas data frame. So to convert from Spark internal format to a pandas data frame internal format, there has to be a copy and convert phase, which is very damaging to the performance in like in these kinds of high performance scenarios. So with arrow, there is it is gone. So if all the systems that we use for big data processing understand the language of arrow, they can read in arrow, and they can they can read in arrow, stored in arrow, and any other system that understands arrow can directly read it without any need to copy or convert. So the data is placed in the memory only once, and the other systems can see it and manipulate it as however they want. So yeah, that's the in a nutshell about arrow. So arrow is not only a zero serialization, like a zero copy format, but it's more. It has a very extensive query processing or data processing framework built around it. So it has like different modules for such as a binary IPC protocol for transferring arrow over the network. Also our data sets framework that allows encapsulating a set of directory of files and basically run queries against it, queries and like selectivity and projection queries. Also it has a file format module that allows reading different file formats and many such things which are basically the building blocks of any query processing system you would find in today's world. So the star marked parts of arrow are basically which we use for Skyhook. So we use the binary IPC protocol for transferring data from the server to the client. We use the dataset framework to basically expose our implementation to the users. We use the embeddable query engine to apply expressions and projections, and the file format interfaces and the file format and compressor interfaces combined to basically to be able to read different formats, different files with different formats. So yeah, so next I will talk about Skyhook. So Skyhook has a specific design paradigm. So as I talked about, two main things in this project are the distributed object store and the arrow library. So in our design, what we do is that we extend the storage and client layers of the programmable storage systems like Ceph, and this can be also applied to other systems like Deos and miniAOD, wherever there is a programmable interface available. So we can extend the client and storage layers, and by embedding data access libraries like Apache Arrow within them. So so as you can see in this diagram, inside the object store, oh, my mouse pointer is vanished. Oh, anyways, so inside the object store, there we embed the data access libraries, which is basically the arrow access libraries, and so that we can like read in objects inside the storage node's memory and process it right there, and then we can transfer it back to the client to another arrow library which basically can receive batches of arrow data, arrow tables, arrow records basically. So that is point one. So second point is we created a file system like shim inside the storage nodes so that we can easily embed the arrow libraries inside the storage. So arrow libraries, or like most other file formats, understand file system POSIX formats. They don't understand objects. So it is a very thin layer between the arrow libraries and the object storage layer, so that arrow libraries can directly operate on objects. So that it can see objects as files basically. And what we do is that on the third point, which is like the most important, we have kind of a dual interface, which is we have a POSIX interface with CephFS, so that we can just dump in Parquet files or some other files to the storage system during the write path, and during the read path we don't use the POSIX interface anymore because it's of not much use. We just use the metadata from it, and we instead use the direct object access library from the that sits beneath the POSIX interface to read out the data, to basically access the data from the object store by applying the data access library functions on them. So the architecture, that was the very high level design paradigm. Now this is an instantiation of the design paradigm using Ceph and Apache Arrow. So this can be applied to any other set of systems. If there are different data access libraries or different storage systems, we can basically follow the same design paradigm. But for this one, so as you can see on the storage layer, we embed Arrow shared libraries inside the Ceph OSD nodes and Ceph object class functions from the client that uses the Arrow APIs basically to scan the Rados objects. As you can see, the Arrow file fragment API, this is the Arrow access library. We embed it inside the OSDs, and these are basically called by a Ceph object class function that is embedded inside the storage node, and we can just very easily scan the objects that are stored in Ceph. That is all that goes inside the storage node. And the random access object interface is the file system shim that I was talking about. It enables Arrow libraries to understand objects, not only files. And on the client layer, the data, so we expose our implementation through the dataset API by creating a custom format called Rados Parquet file format. So which is basically Parquet files stored in the same way as in normal storage systems, which process on the client, but we just push the processing to the to Rados basically. So that's why it's called Rados Parquet file format. So what it does, it reads some metadata during the read path. It reads some metadata from the Ceph POSIX interface, basically the striping strategy. It converts the file names in CephFS to the object IDs in Rados. So using the striping strategy information, it does that conversion from file names to object IDs. And once it has the object IDs handy, it can invoke a storage function, basically the object class function that is embedded inside the storage nodes on that object. So, and that request goes inside the OSD, it invokes the Arrow file fragment APIs and does all the scanning and everything and returns back the Arrow tables back to the dataset API. So it's like really transparent. You can use the Arrow dataset API as it is. You need to just replace the format from Parquet to Rados Parquet, and that's it. And you can fit in the dataset API anywhere you want without any changes. So that's the kind of the cool part of the design. So that's the architecture. So on the right path, so on the right path for the file layout, what we do is that since Ceph has a upper limit on the size of objects it can handle nicely. So it is 128 MB. So what we need to do is that we need to take, if Parquet files are smaller than that, then it's well and good. Otherwise, if Parquet files are larger than that, several GBs, we need to split it up into smaller files and store each files in a Rados object for Skyhook to access. And it does not really cause any performance issues with that. So next we did some experiments with Skyhook. So here are some experiments with two types of data on disk. One is Parquet on disk. Another we tried just to see was to store LZ4 IPC on disk. So in both cases, you can see with lower selectivities, the amount of data moved around the system is very less. And it's like the percentage improvement is really nice, like more than 50% improvement. So you would ask why the higher selectivities are not seeing that much improvement. So there is an inherent problem in Arrow that we figured out in the meanwhile, is that Arrow is really efficient when transferring data between two processes inside the same nodes, but it's not that efficient to transfer data over the wire. So there is a deserialization problem in that case, and with like higher selectivities where we need to send back more amount of data, more time more time is spent into the serialization into a WAR format, and that is causing a lot of problems. So I will talk more on that in the next slides. So on the CPU usage side, as you can see, Skyhook nicely offloads the CPU usage from client to storage. So the client is totally free, it can do more processing, and while the storage is it is nicely divided between the storage nodes, and basically, yeah, so it's nice, it nicely offloads. On the network traffic side, on using SkyhookDM, you can save a lot of network traffic if you are doing queries with high selectivity, as you end up transferring quite less amount of data. And another cool thing is that since we are co-locating a crash, since we are co-locating compute with storage nodes, the crash recovery and consistency semantics of the storage layer apply just out of the box to the query processing layer. So we did experiment where we crashed the OS, where we crashed all the OSDs one by one in a rolling fashion, just within a few seconds, and the query processing like just dropped for a while and then came back up. It did not crash the query processing. So, and the results were retrieved correctly. So that applies naturally to query processing. And so after we built SkyhookDM, we integrated it with Coffea, the processing framework for the HEP data. So we created a run Parquet job executor method in Coffea to be which can process Parquet files and read from Parquet files using the Arrow dataset API. So using the Arrow dataset API made it easy for us also to integrate Skyhook to Coffee. So we just changed the format from Parquet. So we just changed the string from Parquet to Rados-Parquet, and it worked. So yeah, and that was merged in Coffea, and we are currently trying to build more upon that. So yeah, so we integrated Skyhook to Coffee, and so the problem that I was talking about is currently ongoing. So as we can see, like so Arrow's memory layout is such that when you need to serialize it to a WAR format, where a contiguous buffer is needed, so it needs to do a lot of internal memory copies to do that. So it needs to copy out memory locations from like buffers from different places in the memory into a contiguous WAR format, and that has a very high overhead. So we opened this issue with the Arrow team, and they also were very interested in it, and understood that yeah, the Arrow memory format is such that it's very difficult to change, and this problem would happen. So as you can see, I created some pie charts on the breakdown of a life of a query. So the most of the time goes into, as you can see, in 41.5% of the time goes into serializing the data back into a WAR format, and which is like very degrading the performance very much, as you can understand. So yeah, so that is one thing we are trying to collaborate with the Arrow community and also by ourselves to fix. And also we are currently collaborating with the ServiceX and Coffee team to integrate SkyhookDM into the larger analysis facility ecosystem with ServiceX and Coffee and into the analysis facility. And to check out the work that we did, so there is the GitHub repository of Skyhook. We wrote up an archive paper, and the integration with Coffee, and also we reported several bugs in Apache Arrow. And yeah, basically these are the artifacts of my work during the fellowship. And yeah, I think I came to an end. Thank you very much, and yeah, I'm happy to take questions.
Gordon, you have your hand raised?
Yeah. Sorry. There we go. Okay. Really nice talk. Thanks. Sounds like an incredible amount of work. I had a quick question. I think it was actually on your second to last slide where you were talking about the Arrow's memory layout and how this was causing some performance issues.
Right.
Yeah, I was wondering, there are a lot of scatter-gather algorithms that are used in networking. Is the difficulty that Arrow just doesn't implement something like that as it shuffles things off to the network? Or is there something fundamental about Arrow's memory layout which will be very hard to solve to improve this bottleneck?
That's right. Yeah. So yeah, you pointed out the right thing. So yeah, let me come to that. So when Arrow reads out data from anywhere, from basically any file or any source, any file system, what it does is that it allocates small buffers for every data page that it reads out, like in the memory, and it just and then it just provides the pointers, and it uses the pointers to have a table view over the small buffers that are placed here and there in the memory. And that is fine, that works fine as long as we do not move that data. But as soon as we want to move that data without any scatter gather approach, like just in a contiguous buffer, most transport systems like network transport systems accept, so that causes the problem right then and there. So we need to like do very small memory copies multiple times and to create a contiguous buffer. So the solution to this is really the scatter gather approach, where we can basically point to the different, like we can point to the different memory addresses, and the network card, the network card basically need to support scatter gather so that it can read from different areas in the memory and just transfer that. So yeah, so we came across a nice paper recently called Serializer in HotOS, I guess. So yeah, I if you want, I can also share that if you have not already seen it. So yeah, we are basically trying to also take ideas from that, how to implement a scatter gather approach, and without hardware support, if we can do somehow with safe interfaces. Yeah.
Okay, thank you. Very nice.
Any other questions for Jayjeet? Before we move on to the next student, I see that Jayjeet's one of his mentors is connected. Ivo, do you want to say anything about Jayjeet's work?
Well, first, apologies, I got confused with time zones. I just want to comment on Jayjeet's excellent work. He's an amazing student. And I don't know if he mentioned it, but he's going to join UC Santa Cruz this fall as a PhD student. He's going to be working with Carlos, and we're looking forward to having him and keeping him in the IRIS-HEP community as part of now as a PhD student.
Yeah, looking forward. Thank you. Thank you, Ivo.
All right. Thank you, Jayjeet, and thank you, Ivo, for your comments and your mentorship. Next, we have Max. Max was mentored by Jacob Blomer. Jacob, do you want to say anything about Max before we get started?
Yes, thank you. Yes, so Max was co-mentored by Dan Riley and myself. Max is studying at the University of Ottawa. He has undergrad degrees in mechanical engineering and computer technology, and is now doing a master's in mechanical engineering, focusing on radiation modeling. He has been in touch with the root team last year with the Google Summer of Code program, where he worked on RNTuple. RNTuple being the R&D on the future of the T3 IO. And now in this IRIS-HEP fellowship, he was involved with both the root team and the CMSSW team, represented by my co-mentor, Dan Riley. And as a result, it's the first time that RNTuple code runs in the context of an experiment framework. That is something I'm very excited about. So thank you very much, Max, for your excellent work. It has been a great pleasure. And now I'm looking forward to your talk.
Yeah, the pleasure's all mine. Thank you very much. Just looking to share here. Is that okay?
Yep, that's fine.
All right. Okay, yeah. So thank you very much for that intro, Jakob. Yeah, so it's been my absolute pleasure to work on this project. So this is RNTuple NanoAOD output module, and as Jakob said, it's him who's the RNTuple lead, and also Dan Riley, who's a CMSSW expert, and they're both here today, I believe. So yeah, jumping right in. There we go. Okay, so I'm going to do a brief introduction to RNTuple, and then we're going to talk about the output module and some of its characteristics and some limitations that we're hoping to overcome in the next in the future work. We're going to do some file size comparisons between the existing NanoAOD output module that uses T-tree and the new RNTuple one. And then we're also going to go over some read throughput performance for analysis. And we're going to be looking at a variety of storage media here. So some spinning disk results, some SSD, and Ceph results as well. And finally, I'm going to wrap up with the next steps for this project. So RNTuple is the experimental evolution of Root's columnar I/O subsystem. So the successor to T-tree. And so RNTuple here has the benefit of T-tree's long production use, so 25 plus years of production experience for T-tree, but also an opportunity to incorporate some clean slate improvements into RNTuple. So we see it as sort of a modern implementation as a base for future improvements. So things like first-class object store support, which might be difficult to integrate into a legacy implementation. And our main goals for RNTuple are the improved performance characteristics, so reading, writing, and file sizes and all that good stuff, but also robustness, so making sure that the APIs are very easy to use correctly and hard to use incorrectly, and so, but without compromising performance, of course. So it's the goal is, improve them both at the same time. And Jakob has a very nice presentation called Evolution of the Root Tree I/O with much more details about RNTuple and sort of the nitty-gritty of the project. So why CMS NanoAOD? So our project goal is develop this output module using RNTuple to validate the RNTuple library in the context of a large production framework like CMSSW, and also a realistic comparison between T-tree and RNTuple. And so we've developed an output module that's capable of writing the main data of a NanoAOD, and that's the events tree. So with the caveat that backfilling of columns is not supported yet. I'll talk about that a little more later. And to make sure our implementation is doing what it says, we've verified our implementation using a tool to compare files generated by T-tree and the RNTuple output modules, and this ensures that all the data for every entry, all the data is matched and lines up with its counterpart. And we're hoping to integrate this into CMSSW on the short term. So thanks very much to them. They've been very helpful with pointing out things that we can improve and what's needed to integrate into CMSSW. So jumping right into some storage comparison between the two output modules. So we're looking at average event size comparison using LZMA compression. And so here lower is better, and RNTuple is in red and T-tree is in blue. And so what we see is that there is a reduction, pretty consistent reduction in average event size. Oh, excuse me. Sorry about that. Another rookie mistake. Sorry about that. We see an average event size of 1.6 kilobytes for RNTuple, and for T-Tree, it's more like 1.9 kilobytes. And these first 5 samples are Monte Carlo simulated data, and the last one is actually real data. So it explains the discrepancy between the sample sizes. And looking at percentage reduction of event size, we see it's pretty consistent, 16% reduction for all of these samples. So this is compared to the current T-Tree output module that's in use. And T-Tree has a lot of tricks up its sleeve, and it's possible to do improved performance or improved results with new APIs that are introduced by T-Tree. But this comparison is more just sort of showing the same improvements can be realized using RNTuple, and there are other improvements as well. So looking at read speed and analysis performance, we're going to be looking at our NanoAOD dimuon spectrum analysis. So there's in this file there's 1.6 million events, and we're going to be looking at 140,000 of them, and it's a sparse read analysis. So we're out of the 1,500 branches, we're only going to be looking at 6. And these benchmarks are done on a dedicated server. So this is a 64-core machine, and we're looking at SSD, hard disk, and a Ceph setup as well. So looking at the SSD cold read throughput results, this is 1 million events per second, and our 4 quantities here are serial LZMA, multi-threaded LZMA, serial Z standard compression, and multi-threaded. And what multi-threading means for the RNTuple case is as a file is separated into columns. These columns, so columns of ints and floats, are divided into pages, which are in the jargon it's a T-Tree basket. So these pages are being decompressed in parallel. And what's nice about this is it's not limited by the number of branches. So we're not limited to a 6 times throughput increase for 6 branches, because it works on the page level, which is one layer down, I guess. So looking at these results, so we have serial LZMA is the slowest. So RNTuple does offer an improvement over T-Tree for this case, but it is still the slowest, and the trade-off is better compression ratio for LZMA. Moving to a multi-threaded case, we have RNTuple's throughput has a nice boost here from multi-threading. So we go from about maybe 1.5 or 1.7 to a little over 13 million events per second, whereas T-Tree's performance doesn't improve similarly. So moving to Z standard, the serial throughput for Z standard is better than that of multi-threaded LZMA, and the same is true for T-Tree. So both the compression algorithm has a large impact on throughput here, and then the best performance is offered by multi-threaded Z standard for RNTuple, and again we see this jump because of multi-threading. So moving now to our spinning disk results. This is again cold read throughput. So the y-axis has changed a lot here, and we're getting less throughput compared to SSD, but we still see fairly similar trends. So serial LZMA for RNTuple beats that of T-Tree, so it's about 3 times more throughput for the serial case. And going to multi-threaded, RNTuple also has an improvement from the parallel decompression. And then we see sort of an interesting result for the serial and multi-threaded Z standard results, where it's actually less than that of multi-threaded LZMA, and we're attributing this to the being limited by the I/O device. So the disk head is just not fast enough to get better throughput, because LZMA is a smaller file on disk than Z standard, so we have more volume read for the Z standard case. So it's sort of interesting. And then for T-tree, Z standard also has this result where it's actually worse throughput than LZMA. And finally, we're looking at Ceph, and this is a warm read throughput. So we were sort of advised to discard the first result and take the average of the next 10. And so compared to spinning disk, this is very good. So again, for serial LZMA, our throughput is improved over T-tree, and moving to multi-threaded, again, there's a good performance boost from multi-threading. Again, the serial Z standard is again an improvement over multi-threaded LZMA for throughput, and there's a much smaller, noisier increase in multi-threaded Z standard for this case. So we're going to be looking into improving our multi-threaded performance. For 64 cores, we should be getting a better improvement here than what we see. And for our next steps for this project, we're really hoping to get integrated into CMSSW, so we're working on that. And hopefully it'll get merged in on the short term. There's one of the things that's stopping us from production use, or one of the production requirements, is support for this backfilling of columns, where right now for RNTuple, you need to define your schema ahead of time. But for NanoAOD, there are these branches where you need to, you don't know if you're going to generate them or not before you start writing. So this is something we're hoping to support using this friend mechanism. But there's also an upcoming revision of the RNTuple file format, which will allow for backfilling without this workaround. And we're also going to complete support for our NanoAOD auxiliary trees. So we're supporting the main, the real meat of the file is the events, but there are also some other trees in there that we need to improve our support for and completely support them. And I guess this one doesn't super apply here, but we're looking hopefully for a NanoAOD open data set, put a request into the NanoAOD group for this data set for performance studies and tools development for projects like this one. And we're sort of working with their feedback on that. So that's all for this presentation. Thank you very much. And if there's any questions, I'd be happy to answer.
David, you have your hand up?
Yeah, hi. It's really fantastic to see this. I see the pull request that you have is making progress, so that should go in soon on the CMS side. I had a question. I think it's on slide 5, just because I know from experience measuring, doing this kind of study is tricky. Can you say how big are the files you're using? Are they gigabyte scale files?
These are probably all, I think the largest one we have is 330,000 events. So we're not on the gigabyte level. It's more like hundreds of megabytes. So that's
okay,
kind
but
of,
in any case, it's hundreds of thousands of events, which
yes,
I think
yes.
means buffers are full. And then the T-tree results, are those also you rewrote? Are you rewriting those files for the T-tree, or I'm presuming these are files that probably came from CMS in some form?
Yeah, so this, I have the exact files if you want, but these are from a miniAOD data set. And let's see if I can pull them up here. So these are our inputs to the NanoAOD module, and we're using the same input for both the RNTuple and the T-tree output modules. So this is a
Oh,
run.
perfect. So you're creating, okay, perfect. You're creating the NanoAOD and by yourself, so it's a fair comparison. Yeah,
That's right, yeah.
There's tricks in the way NanoAOD gets produced in production, so you've done the right comparison, so that's great. Thanks.
Okay. Yeah. Yeah, thank you.
Gordon, you had your hand raised?
Yeah, Max, great talk. And I agree with Jacob. It's really wonderful to see RNTuple and you working with a large scale experiment like this. And I'm looking forward to an update eventually of these results with many gigabytes, as David was saying. I also love that you're at University of Ottawa. I have some connections there, so that was pretty cool to hear. So I got two questions. One, you didn't really, I don't think you really mentioned it, but David obliquely referred to it in the sense of this pull request. How much work was it to add this to the CMS infrastructure? Is there something about RNTuple that felt really different from T-trees and this required a different programming approach? How much effort was it to integrate this in?
Yeah, that's a great question. So a couple things, I guess, is the first is I really didn't have any experience with CMSSW before, so at least, and I had a lot more experience with RNTuple, having worked with it in the past. So this is going to be a little bit biased,
Sure.
but there is a lot of work going on to make sure that the similarities between RNTuple and T-tree are pretty self-evident. So I would say, at least from an implementation point of view, there is usually an analog between the APIs that you want to use. So adding branches or fields in RNTuple is fairly similar and requires less manual bookkeeping than in T-tree. Whereas sometimes in T-tree you need to make sure that the address of a vector you're filling hasn't jumped around in memory. So there are definitely improvements there, but the backfilling was sort of a limitation that we encountered, where there's a requirement for it, and as of yet the API doesn't support it. So that was sort of a challenge, and that was the thing where it was like sort of required the biggest divergence. But we're really hoping to address this and make sure that implementers don't run into this into the future.
Well, this is the beauty of trying to put this into something like the CMSSW, is that you'll find these gaps and these missing things that either need to be taken care of or designed around. And I had one other very quick question. In your speed comparisons, it looks like, and it doesn't matter which speed comparison, but all of them show the same behavior. The T-tree moving from single-threaded to multi-threaded has the identical performance. And that caught me a little off guard. I could have sworn I've seen T-tree support for multi-threading where it actually improved the throughput, but that certainly is not showing up in your plots. Am I misremembering this is not my area of expertise, but am I misremembering, or is there something else going on here?
Yeah, so what we think is going on here, and what we're pretty sure is going on, is that the benchmark setup is a sparse read, so we're only doing 6 out of all these branches, and T-tree is the multi-threaded case is limited to this 6. So you can only look at one branch per thread, basically, whereas RNTuple does not do that. So they go layer down and look at pages, and I think Sorry. Yeah.
Sorry, just are the T-tree files not written in split? You know, have they been split out into columnar, or are they written sort of event record like?
I believe these are columnar.
Okay.
Yeah.
All right.
And
Okay.
so I don't. Sorry, I don't think. I hope the takeaway isn't that T-tree is slow in parallel. It's just I think this benchmark just kind of plays to a strength of RNTuple and maybe not so much to T-tree in multi-threading.
Okay, perfect. Thank you.
Yeah, I think that it's true that the multi-threading of T-tree is somewhat limited, and maybe Jakob could comment, and that's why we wanted to investigate RNTuple, which was from the ground up. Multi-threading was part of its aim.
Yeah, sorry, Liz. I didn't mean to say I'm sure RNTuple is faster. I'm just surprised there's no improvement in T-tree. That was I would expect it to be the improvement not to be as much as RNTuple, but I would have expected some improvement from what I've seen within Atlas. That's all.
Yeah. No. The analysis formats are supposed to be written out full split unless something's changed in the very recent past. So I'm pretty sure something like a miniAOD would be fully split. Yeah, this is great work. I'm glad to see it. I was very interested when I heard that this was happening before you started, and now to see the result, that's great.
Well, thank you.
I do have a question about your kind of results slide, or the very last slide.
Yes. Next steps or one of these?
Yeah, the next steps.
Okay, yeah.
So I see that you're already using an ultra legacy data set for the raw, for your real data input one. And is it just that there is, so I guess I'm asking, is this a policy thing that you have to request this NanoAOD open data set, or is this a technical thing, like that they haven't made a NanoAOD yet from the miniAODs? Do you know?
Not entirely sure. Jakob, are you?
Maybe Dan is the best to answer this.
Yeah. If you don't know, it's not a big deal. I've just
this is the usual. Interesting data formats aren't readily available outside of the collaboration, right? So you need me or Dan or someone to copy some files for you and use them. Use them without telling anyone that you're using them or whatever you want to do.
Oh, okay. Yeah, I mean, if it's just a few, if you don't need a large volume, I would think that would be possible. But okay.
Yeah, the open data has lagged pretty badly, and we did get max one file of real data that there was a comparable open data file for.
Yeah, I mean, I do know of an effort in the data preservation group of, if you needed large scale of people trying to take the run one data and create NanoAODs out of it. And then you would have large data sets. Right?
So I'll just jump in. There was an effort, one of the other fellows that was working on this. I don't know if Jim wants to address it, but
that's what I was going to say.
Go ahead. You want anything else, Jim?
Well, sure. So before this, on splitting in NanoAODs, the NanoAOD format is such that splitting has no effect. It's been manually split. So it's effectively all split. Now on the availability of NanoAODs for open data, they are not being served as NanoAOD. They're being served as Run 1 AOD. The NanoAOD conversion tools, the that are used in Run 2 production require Run 2 miniAODs, so it's not compatible. The Open Data Group has developed a NanoAOD outreach tool, is the name of it. It produces formats that are like NanoAOD, and also a full NanoAOD for full, with feature parity with Run 2 NanoAOD is in development. The files themselves is still, if you want to make Run 1 NanoAODs, it is still the case that you have to make them yourself. This is what Brian Cruz was working on, and also what Gordon Baidyanath was working on this too through ServiceX. This is that.
I see.
But and it would be ideal, I think, if the data preservation would just supply NanoAODs as like one of the data tiers that's just provided, especially considering that it's less than 1% of the size. It's a much smaller.
My conclusion from it, just to be clear, is that one way or another, we'll just make it happen.
Yeah,
I think there's enough motivations for it. We just,
Yeah, no, it hasn't yet gotten to the pressure of the amount of disk CERN's willing to give us for open data sets is, really motivating a reduction of size yet, but I'm sure it will get there eventually.
Yeah, the obstacle has really been just somebody doing it, I think.
Yeah. Mm-hmm.
We'll make it happen somehow.
Great.
I see Nick, you have your hand raised. Do you have a question?
Yeah, this time. I was curious if you could elaborate a bit on the auxiliary trees, because this is kind of one of the use cases that I find a bit awkward with T-trees and the way NanoAOD works, because basically, right, you have some data that spans multiple events, right? But T-tree is very fixed on this one row per event concept. But as I understand it, at least RNTuple is not so strictly tied to that, right? You can imagine having, multiple, spans, let's say, of rows, just holding a single value, so that you wouldn't need these auxiliary trees to track such things. I wonder, is it possible to do that in RNTuple, where you wouldn't need these extra trees that just hold per file information or per LUMI section information, and just would have that as part of the NTuple, with the same interface, assuming the backend is, of course, only storing the minimum required amount of data.
Yeah, so I might flag Jakob in here, but for right now, we're just trying to match one-to-one. So our auxiliary tree storage is entry by entry. I think there is an effort to have these arbitrary sort of key value pairs stored in RNTuple 2, but I think at least right now it's pretty tied to entry per event.
Wait a minute, actually Nick's comment can be very nicely served. Maybe Jakob wanted to say something about this. Very nicely served by the RNTuple format. The new format would allow you to have doubly jagged, so doubly lists of lists in a very natural way that's still fully columnar. And then what Nick wants with, say, one entry is one LUMI block, and then events are inside of that, and then particles are inside of that. Sorry, I jumped in. Maybe Jakob wants to say something.
I think, you're right. The format allows for that. I think we were up to this point not audacious enough to try and rip it apart in this way and to move away from the strict coupling to an event.
Well, I think there's some motivation to it, right? If you look at things like our data frame, where you are expected to deliver one particular RNTuple, right? And so to be able to join the information from these auxiliary ones in our data frame, you either have to like create some special, you know, utility in our data frame to map them up, or you make the interface at the NTuple level and you just specify whether you want to loop over, you know, the first level of indexing, e.g. the Lumi block in Jim's example, or the second level of indexing, which would be, you know, the event level, or even the third level. Maybe you want to process one jet at a time.
Yeah, I guess it is right. As long as you stay like end-to-end columnar, that works fine. It falls on your feet the second you have you want a row-wise access. But this is right. Probably for analysis, we never have this. We have end-to-end columnar access, so that might actually work nicely. Yeah, thanks. We'll think about it.
Dan, you had something you want to say?
Yeah, not a question. I just wanted to thank Max and Jakob. It was a real pleasure working on this project with them. And I was very excited that we got input into RNTuple on the integration of the CMS framework. I think that was really nice.
Thanks a lot, Dan. Yeah, it was a blast. Thank you.
Liz, you have your hand raised?
Yeah, just to follow on with that, I think this is also very impressive work. And I was just wondering what, Max, your future ambitions are. What's next for you personally?
I'm not entirely sure. Really trying to finish up this master's, but afterwards, I'm really basically open to a lot. So nothing concrete yet, but
okay.
Yeah, it's been really great working with Jakob and Dan. It's been a lot of fun. So thanks.
Good.
All right. Thank you all for the questions and the discussions. Thank you, Max, for your presentation, and Jakob and Dan for your mentorship. That's all we have for today. So thank you all for coming, and hope to see you next time.